In 2022, a team of astronomers pointed the James Webb Space Telescope at a small patch of sky. The patch was about the size of a grain of sand held at arm's length. They left it running for hours, and when the data came back, they found galaxies. That's not surprising. Webb is the most powerful space telescope ever built. What was surprising is where those galaxies were, or more precisely, when. Light takes time to travel. When you look at something a billion light years away, you're seeing it as it was a billion years ago. So a telescope powerful enough to see very distant objects is also a telescope powerful enough to look back in time. Webb can see so far that it is collecting light from galaxies as they were near the beginning of cosmic history. Galaxies that formed only a few 100 million years after the Big Bang. And nobody was ready for what it found. The universe is 13.8 billion years old. For the first 380,000 years, it was too hot and dense for light to travel freely, a wall of glowing plasma. Then it cooled, hydrogen formed, and light could finally move. That's the cosmic microwave background, the oldest light we can detect. After that, nothing. No stars, no galaxies. Just hydrogen and helium gas, very slowly being pulled together by gravity. This period is called the Cosmic Dark Ages. It lasted somewhere between 100 and 250 million years. Then the first stars ignited. Then, gradually, those stars clustered into the first galaxies. Gradually is the key word. Building a massive galaxy takes time. Gas has to collapse under gravity. It has to cool. It has to fragment into stars. Those stars live and die. Their remnants enrich the surrounding gas with heavier elements. New generations of stars form. Galaxies collide and merge. The whole process is slow, and there's a physical ceiling on how fast it can happen. Even under the most optimistic assumptions about star formation efficiency, you cannot build something truly massive in just a few 100 million years. Our best cosmological model, called Lambda CDM, makes very specific predictions about this. It says what the most massive galaxies should look like at different points in cosmic history. And for decades, every telescope we pointed at the early universe confirmed those predictions. Then Webb found 6 galaxies. 6 galaxy candidates, seen when the universe was roughly 500 to 700 million years old. And the mass of these galaxies, the total mass locked up in stars, was enormous. One of them appeared to be as massive as the Milky Way. Another appeared to contain more stellar mass than the Milky Way. One reached an estimated 100 billion solar masses. Lambda CDM says the most massive galaxies at that age should have at most roughly a tenth of that mass. Some of these candidates are off by a factor of 100. In the small volume Webb surveyed, even one object like this would have been hard to explain. 6 made the math considerably worse. Now, measuring galaxy masses at high redshift is genuinely difficult. You're working with faint, distant objects, and you're trying to infer mass from brightness, which requires assumptions about stellar ages and compositions. Some of the most extreme estimates were revised downward as more data came in. But revised downward is not the same as resolved. The tension with the model is still there. Multiple independent teams, using different instruments and different analysis methods, keep arriving at the same place. So what could explain it? One option is that star formation in the early universe was far more efficient than anything we observe today. Conditions were different back then. Higher gas densities, almost no heavy elements, no accumulated feedback from previous stellar generations disrupting collapsing clouds. Maybe under those conditions, gas turned into stars at rates that simply have no modern equivalent. That would mean the model doesn't need to be replaced so much as extended to cover physics we haven't worked out yet. Another option has to do with the stars themselves. In the early universe, with almost no heavy elements, the first stars are thought to have been much more massive than typical stars today. More massive stars are dramatically brighter. So a galaxy full of them would appear more massive than it actually is when you estimate its mass from its light. You'd be overcounting. Some of the discrepancy might be a measurement problem, not a physics problem. There's also the possibility that our models of dark matter need revision. Dark matter forms the scaffolding that ordinary matter collapses into. If dark matter halos in the early universe were were more concentrated than Lambda CDM predicts, or formed more quickly, galaxies could have assembled faster too. None of those explanations require touching the model itself. Lambda CDM has been extraordinarily successful. It correctly predicts the large-scale structure of the universe, the distribution of galaxies across billions of light-years, the acoustic peaks in the cosmic microwave background. It is held up under decades of scrutiny, but it was built on observations of the later universe, not the first few 100 million years. Webb is the first instrument powerful enough to actually test it there. Maybe the model that works beautifully from 1 billion years onward simply doesn't capture something real about how structure formed right at the start. What makes this hard to set aside is the pattern. It's not one team, one paper, one unusual galaxy. Survey after survey is finding more structure in the early universe than Lambda CDM predicts. The more Webb observes, the more consistent the picture becomes. One of the researchers involved put it plainly. Finding one galaxy like this is interesting. Finding dozens is a pattern. That said, none of this is settled. Systematic errors in mass estimation at high redshift are real and not fully understood. Dust affects these measurements in ways that are hard to account for. The most striking claims from 2022 and early 2023 have been walked back somewhat by follow-up work. But even after all that, the tension is real, and it isn't going away. Before Webb, the first few 100 million years of cosmic history was essentially a blank. We had the cosmic microwave background on one side, and reasonably well-studied galaxies on the other, with almost nothing in between. Everything the model predicted about that gap was extrapolation. We had no way to check it. Webb is the check, and right now the check is coming back wrong. Either something about early star formation and galaxy assembly is different from what we assumed, or something about the underlying model is incomplete. One of those changes the astrophysics of the early universe. The other changes cosmology. Both matter. We don't know yet which one it is. Webb is still early in its mission. The data is still being analyzed. Better measurements are coming. But here's the thing. We built a telescope to see the beginning of time. We pointed it at the oldest, most distant galaxies we could find, expecting to confirm what we already believed. And the early universe wasn't what we thought it was. I've left some book recommendations in the description. And on the end screen, 2 more videos on the same kind of physics. Thanks for watching. See you on the next one.